as Dr. Sujata has already explained briefly on the satellite data processing, but we will go in little more detail. Here I put satellite image processing because mostly I will deal with the images rather than data, because satellite gives you data as well as images. So data processing, when we talk about, which includes images, but exclusively today I talk about on the image processing. Data is like ancillary data also we receive, and then navigation data we receive. That processing we are not dealing with right now. But however, wherever that is useful in our image processing, that I will just touch upon. First, hopefully you all may be knowing about general image processing. Hopefully, I thought it is a computer science department. Definitely, you may be doing, you may be knowing already certain level of image processing. But one basic question: what we do, why we do the image processing? It is basically because we wanted to understand the image. It is because image understanding is the key. When the image is given, you have to understand. So you need some tools. What are developed under image processing is image processing tools. So just remember that no tool is generic. There are image processing tools, but they will not be, basic is okay. But when you apply for various images, when you talk about astronomical images are there, and then satellite images are there, X-ray images, many images are there. For each image, the processing parameters will be different, though the basic tools are same as image processing tool, enhancement, restoration, all those things. But the parameters are different. So depending on the application, you need to tune your image processing algorithms towards that. That is the key. So one, do we need an image processing is because you wanted to understand the image. So it is for image understanding. Finally, an image is given means which you wanted to understand fully. Then what are the sources of images? You already know. One is from satellite, aerial, and various platforms. When I say X-ray image, gamma ray image, many images are there. So even the electron images, many images are there. So for each image, the processing algorithms you need to tune. So let us start today. It is basically how the satellite image is acquired and what is satellite imagery and what are the aspects like pre-processing and then value additions and certain image the research topics also. So because once we talk about to students or faculty and all, you will be more interested in not only processing techniques but what are the research avenues available under this field, then certain applications, and at the end, since it is related to the planetary and all, I also touch some of the planetary and science missions of ISRO. So because this is additionally which I have put because Madam G. Radhamani told me that the seminar is for the planetary sciences. So better some introduction on the planetary missions which ISRO has already developed. Those things also I wanted to just touch upon. So let us go through the presentation now. First, bring it, what is the remote sensing? Because all the satellite image processing comes because of the remote sensing. Satellites are in the sky. So remotely you are sensing the information and then processing. So first let us understand what is the remote sensing. There are many definitions, but they'll see the third definition which is most applicable today. As remote sensing is the art, science and technology of obtaining reliable information about physical objects and the environment through the process of recording, measuring and interpreting imagery and digital representations of energy patterns derived from non-contact sensor systems. See, the basic term remote sensing itself says that you are sensing remotely. That means you are getting information remotely on an object. That is a simple definition one can understand. Modern way to do all these things, that collecting information and all without touching the object, all those things, this definition you can easily see that. So this is what is the remote sensing all about. So remote sensing can be done now today many ways. You see, you can do with satellite, you can do aerial. Today, the state of the art is the drones. So you can send without any, you are sitting here and then you can send a drone and then you can collect the information. So this is all remote sensing. So let us talk about what the imagery you will get it and how to process from the satellites today. So, principles of satellite remote sensing. Here I am giving you in a brief. So you can see here there is a passive and active remote sensing. Passive means what? The source is the sun, where the reflected energy source is the energy source is sun here. Then what you do remote sensing is interaction with the targets. So the energy, electromagnetic energy interaction with the targets, and receiving those signals. You can see in the diagram, one is the energy source of the sun. It is giving you the electromagnetic energy where it is interacting with the target, and the radiation will be, you can see that it's radiated and then reflected and scattered. Incoming EMR, reflected and emitted, all are collected at the sensor situated at satellite. So this is the interaction of electromagnetic energy with the targets is the key to the remote sensing. Okay, so once the energy is recorded in terms of imagery or in terms of signal, when you say microwave or radar, it is only a signal. When you say imaging, it is an image there. So like CCD camera, if it is there, it becomes a image. So once you collect that, you transmit to the ground station. What you can see here is the one ground station is there, which is the antenna, and after that it will be given to the interpretation and analysis and application to the computer processing. This is the principle of remote sensing. You can just see that this gives you a very clear picture. So the passive energy or electromagnetic energy, you collect the on interaction with the targets. It can be reflected, it can be emitted. Those energy you collect on the satellite and then transmit back. And in the form of signal or in the form of imagery, you can collect and then analyze that. So this is the principle of satellite remote sensing. So some basic concepts when you talk about on the satellite image processing or satellite remote sensing, the sensors on board the satellites are similar to the eye in the sky. What we call it as eye in the sky we call, because the sensor is seeing a very large view on the earth. So in a synoptic view you are seeing, so we call this as a eye in the sky. And you can see that the remote sensing technology tries to simulate the process in a very efficient manner, see the natural resources on the planet Earth, or it can be planet, any other planet. Even you talk about whether it is Moon or Mars or any Venus, all the missions when they go there, it will be only taking a remote sensing imageries or remote sensing signals and analyzing various aspects. So this is the electromagnetic spectrum normally we use for the remote sensing. You can see here is the visible, near infrared, mid infrared and thermal infrared, microwave. These are the various bands which we use for the remote sensing imagery or technology. And here one definition you can see that satellite moves around the Earth or any planet in an orbit, what we call. So if the orbit is low Earth orbiting, that is between 600 to 950 kilometers, it is called the LEO, that is low Earth orbit. If it is at 36,800 kilometers, it is called geo Earth orbiting or geosynchronous. That means like all our INSAT satellites are geosynchronous. That means they will be seeing only one part of the Earth, because satellite rotation as well as Earth rotation, they are exactly same. So relatively they are not moving. So satellite always sees a particular area on the Earth. Like for INSAT, India is the focus. So for communication satellites, so you always see India. So that is geo Earth orbiting satellites. There is one more MEO, middle Earth orbits. All the navigation satellites which are at 22,000 kilometers, they are called the MEO satellites. That is middle Earth orbiting. So these are the three categories: LEO, MEO, and GEO satellites. Okay, when the remote sensing satellite goes in an orbit like this, we can see a sketch here given. the detectors, that is CCDs in the camera on the satellite, and how it sees on the Earth. You can see a small area on the Earth only it will be covering, because at 900 kilometers or 600 kilometers, you will cover only a small area on the Earth, which is called the swath. And each detector sees certain distance on the Earth, which is called the sampling distance. And for one line, if number of detectors are 4,000, let us say 4,000 pixels you will get, and then for like that, as satellite moves, different lines are acquired. So this is the way you form the image. Okay. So here a little more detail. You can see that swath means the width of the area what it covers in a particular orbit. As satellite revolves around the Earth, the sensor sees a certain portion of the Earth's surface. The area imaged on the surface is referred to as a swath. Then geostationary, what I told, it is always on a particular area focused, because the Earth rotation and the satellite in the orbit, the speed is same. So it always be looking on the same place. So this is called the geostationary. Then polar orbit, all the LEO satellites are polar normally. So you can see pole to pole it will cover. As Earth moves, it covers different area. So the full globe is covered in this case. As Earth moves, the next swath, next swath, next swath, like that, total globe will be covered with this. So polar orbits will have inclination of the orbit relative to line running between the north and south poles. Many of these satellites' orbits are also sun synchronous. Meaning is, in the morning, suppose at 9:30 it visits a particular area, it visits the same area on the same latitude with the same time. So like 9:30, it will visit to the same latitude every day. That is called the sun synchronous, such that they cover each area of the world at a constant local time of the day called local sun time. And ascending and descending passes. As you go from pole to pole, in some portions of the globe, satellite comes from top to bottom. Some portions of the globe, satellite goes from bottom to top. So these are called the ascending and descending nodes. Because when you go from top to bottom, it is ascending. When you go from bottom to top, bottom to top is ascending and top to bottom is descending. So this is, you can see that satellite platforms are near polar, which means that satellite travels northwards on one side and towards the south pole on the other second half of that. These are called ascending and descending passes respectively. Then there is a passive and active. As I told, how these sensors are sensing. If sun is the source of energy, then it is a passive remote sensing. Whereas if you are sending a signal and receiving back its reflectance or radiance and all, then it is called the active. That means in an active, you will send a pulse and then receive the interaction of the object, whatever is the energy back. That is what is the microwave and LIDAR, radar and sonar. These are the principles. It will send a signal and receive. And whereas in Aster, Landsat and our IRS and all, they are passive sensors. That means sun as the energy source in this case. So that is the difference. Then now you can see that sensor types. What are the sensor types? There are optical sensors. That means they are in optical domain, optical wavelength, electromagnetic and microwave. So in that also there is an active and passive. In optical, in the active mode is the LIDAR. And optical passive is radiometers. All satellites which we have today, all are mostly in radiometers and all imaging spectrometers. These are all passive. The microwave, if you see synthetic aperture radar, that is an active. You are sending a pulse and then receiving scatterometers and altimeters. Whereas passive are multi-frequency microwave radiometers. So these are the categories of sensors on the satellites which you use. So don't discriminate now whether I'm talking about on the Earth or even various other planetary bodies also. Depending on optical microwave, these are the things. But there are other sensors which are actually X-rays and gamma rays spectrum, spectrometers, they are there, they are different. So that I am not talking in this lecture, but mostly these are optical and microwave. Most often we concentrate on the optical imagery because microwave is another big domain which a full topic one can talk. So now there's key steps. Anyway, this I have already explained in the sense you see that sensor in the bottom left corner is the sensor data collection, and it will go to the receiving and processing, that is an antenna. Whatever dome you are seeing is an antenna, and there is an image generated, quick look, then image data you generate, and storage and human compute. This is the same thing what I already explained you. So this is a type of imagery what you have today as an image. If you talk about one is panchromatic, that means only a single band image. Suppose if you say that in the visible band 0.4 to 0.8 micrometers, so this is one single band. There is a multispectral image where you can get the same band sliced into three, red, green, blue, and assign three different colors. You get multiple tones. So the advantage being the first one is black and white, so our eye can only sense few tones. Whereas in the color, you can see that several tones you can see, where the interpretability of this image is much, much better. The third image down, if you see that, it is a SAR image. Actually, SAR sensors send only the signal to you, which you will reconstruct on the ground the image. Whereas in optical, image is on board itself, which it will be only transmitted. So that is the difference. SAR is more complex because complex signal you will get where you will be converting into the image and then processing it further. And rightmost, if you see, today's context is hyperspectral image. Today in the advanced mode, when you talk about the hyperspectral or superspectral, when you talk about, that means the whole spectral band is still further sliced into very small bandwidths, so that a discriminability of the feature increases many fold. But the disadvantage is the signal strength here will be very, very poor, because you are getting the spectrum chopped off into a very small nanometer bands. The signal will be very, very weak. So there is a lot of challenge in the hyperspectral image, but the information content is more in the hyperspectral. So there is a trade-off, the sending, and even if you wanted to do a classification now, suppose hyperspectral means there are 512 bands. If you wanted to classify, it would be too difficult. But there is an image processing challenge there. Which bands you have to select out of 512? Optimal band selection in the hyperspectral. So this itself is a big topic of interest which people study. And SAR image processing itself is a big study. So you have several studies as you go along with the satellite image processing. You will get many more research topics out of it. So when I talk about these imaging capabilities, just to give you a simple idea what our ISRO capabilities today, if you see that, we started at Bhaskara in 1979-81. You can just go how many satellites, what are the kind of sensors we have launched, and then what are the resolutions what we have in each case. You can see that 1988 we have got first operational remote sensing satellite IRS-1A with 72 and 32 meters, 72 meters resolution, 36 meters resolution. Like that, just to give a gamut of things here, I just put up to 2008 here, Chandrayaan-1. Then the next slide, if you see 2009 OceanSat 2, and we have gone up to Cartosat 3. In 2019, we have launched it as a 0.25 meter highest resolution today. Even in the global, nobody has 0.25 meter resolution. So this many satellites we have, and then in the future, anyway, NISAR, which is actually NASA, ISRO synthetic aperture radar. In fact, due to our radar capabilities, they have collaborated with us, and then they are giving one sensor, and our satellite is ours. And NISAR is actually joint venture between ISRO and NASA. So, madam, is it okay? I'm audible now, just to confirm.
Yes, sir. Yes, sir.
Fine. Okay.
Fine, sir. Fine.
So now I will go to the image acquisition modes just to give you some idea how the images are acquired. There are frame images, whisk broom imaging, push broom imaging, step and stare, stereo imaging, wide mono imaging, TDI imaging. These are various categories. Just I'll give few examples to show you how the frame imaging looks, in fact. Hope you are seeing it. See the satellite as it is moving over the on the surface. You can see that surface it is taking frame by frame and covering the entire earth swath from one end to another. That is called the frame imaging. That means each time you are covering one frame, next frame, as satellite moves forward, the whole swath is covered across the top to bottom. Then the next one, what whisk broom imaging, what we have. These are little like Landsat and all they used to use. Here you can see that first left to right, some few scan lines, it will be keep taking it, and continuously as satellite moves, it takes the imaging and the whole entire swath is covered. So this is called the whisk broom imaging. In Landsat TM and all, this is being used, in fact. So each one has its own advantage or disadvantage, as well as the technological aspects are during that time, whatever is there, they have used, in fact. Today, what we use, we use this push broom imaging. This is a push broom. The term itself, if you say, as satellite pushes forward one line and it brooms. Line by line it takes. As satellite moves, it takes line by line. So that's why it is called the push and broom. Broom means just like a house we are brooming, you know, the same thing. Satellite pushes and brooms, pushes and brooms. So this is the usual technology today we use in our all IRS satellites. As satellite moves along with its velocity, it takes image one by one line. Then further to that, push broom only, but step and stair imaging, to get a better resolution, what we make it, more satellite control we take, so that high resolution we get in the orbit. Now you can see that satellite in the orbit itself moves so much, it steps and stares at one point for some time. So it gives you a better signal and high resolution. But the disadvantage is it covers only a small portion of the Earth. So this is called the step and stare. So you step forward and stare for some time, then take it. So this is called the step and stare technology. So in the absence of high resolution sensors, we use this technology as the technological aspect. Then called the stereo imaging. This is push broom technology only, but you put three sensors simultaneously, they see the same ground area. This is on the Chandrayaan, this is on the moon. This is a Chandrayaan configuration. Three sensors mounted in three different angles. The area is continuously covered in stereo. So this is the stereo imaging, what we call. Then there is one more kind of imaging called wide mono. You can see that two cameras can be used as the stereo, or they can be little more, just tilt the camera and make a wide swath. That means this covers a small swath, blue, and red also covers. Together, it will give you a bigger swath. So this is in our Cartosat 1, we have employed this technique. Sometimes stereo you can take, sometimes wide swath you can take. So then other one is TDI image, that is time delay imaging. So this is also push broom imaging only. But you take on the same line some number of stages, like 10 stages. The 10 times the same line you take and integrate so that your signal to noise ratio is much better than what it is. So this is another thing. So now you can see that this is stereo imaging, what I told, the same area covered in 2 different angles. So that that will give you a stereo. We will talk about in the stereo a little more different, a little more detail later on. In Cartosat 1, it is called the operational stereo. In the same satellite, we kept 2 cameras, one at 5 degree, other one at 26 degrees, so that both imagery combinedly gives you the stereo. But today's context, when you talk about this, is actually Chandrayaan right side 3, 4, the 3 cameras are there in Chandrayaan to give it triplet. I will come back to you whether it doublet or triplet, what kind of advantages you get in the stereo data processing, why we need to have. Just you remember here how the data is acquired today. And the Cartosat 2 and today high resolution images, we have various other things, because when you talk about the triplets, doublets and all, there will be a lot of data rate. There are 2 cameras you have to transmit, 3 cameras you have to transmit. You know how difficult it is when so much data transfer from satellite to ground takes place. So now the innovative way is high resolution satellites. As resolutions are very high, the data rates are very high. So what we do, we use very optimally in the same ground, in the same orbit itself, you can get stereo, you can get simple spot imaging, or you can get paintbrush imaging to get a large area. And multi-view, what I put it here is 3 views on the same area, so it gives you the stereo. So now they are now agile satellites, what we call. That means satellite can be tilted very fast and take any area. Today's technology is this agility. Agility means wherever you want it to take, quickly you can take. I don't want the full earth top to bottom, but I want certain portions, like for flood or from earthquake, or when we wanted to detect what happens. If satellite is quickly programmed to take that, that will be most easier. Otherwise, if you wait for satellite to come, and then it will be difficult. So these are the agile satellites which are more useful with high resolution today. Like Cartosat 2 is Cartosat 3. All these things are agile satellites. Even Iconos US satellites, ArcView, all those things are agile satellites. Now, once the image acquisition is over, certain terms you have to define in the satellite images when you talk about resolutions. You may be aware already what are the resolutions, but we talk about 4 kinds of resolutions this time in the satellite image perspective. Spatial or geometric resolution, you know that. Now, anybody know all the cameras and all we know today? You say 20 megapixels, 4 megapixels, 5 megapixels, all megapixels, what we talk about now. What is that? It is actually the geometric resolution, high definition. So it is a geometric resolution. Each CCD sees how much area on the ground. So if 20 megapixels will see very small area. So it will be a very high resolution. Small area you are seeing means very high detail you are seeing. So spatial resolution corresponds to the nominal pixels typically in a meters or in an angle, whichever way it is. So you can easily see that for this you can easily understand. Geometric for each detector, how much area you are covering on the ground. That is the geometric resolution. When you what is the radiometric resolution? These are the number of bits you allocate. See, geometric resolution may be very high, but what is the use if I give only 1 bit? Either it is black or white. So you need radiometric resolution as well to detail to get the more details. That means how many number of bits you are giving to represent a particular pixel. So you have the 2-bit image, 4-bit image, 8-bit image, or 11-bit image. Today, our images are around 10-bit or 10 to 12 bits, so that more information you get. Within small light change also you should be able to get. So that's why it's called, it is actually the radiometric resolution is number of digits what you allocate. Then spectral resolution, as I told, multispectral and all. What is the spectral resolution? It is monochromatic or multispectral or hyperspectral. How many spectral bands are there? They are called spectral resolution. Then temporal resolution is at what interval in time you are taking. Suppose you wanted to see Coimbatore in 1970, 1980, 1990, and how it is changed. So how do you get it? If there are satellites available in 1980, you have a picture of that, and today 1990 also you may have a picture, today also you have a picture, and if you take several pictures on various dates, then you can get the change detection. So these are all called the temporal resolutions. That is number of days needed to reacquire the same image. Suppose if you wanted to monitor a crop, so you need to take at sowing level as well as growing level as well as cutting level. So when you want to take all those things, same area you have to cover at 5-6 different stages. So these are called the multi-temporal. So all are important. Each one is important for its own application. Spatial resolution is important, radiometric is important, spectral is important, and temporal. So you need to understand all the 4 resolutions when you wanted to process the image. Here I have given you a spatial resolution definition like 25 meter, 5 meter or 1 meter. The same similar feature, how it is expanded. More area will be covered in 25 meters and very less area will be covered in 1 meter spatial resolution, but high detail is seen. Spectral resolution, same area covered in 3 different spectral bands. One is in green, red and near infrared.
So the size of the... Can I interrupt, sir? The size of the images will be too high, no, sir? Because you're capturing as images, and if it is color images, how... And you will be having challenges in the storage part also, no, sir?
Right. See, as resolutions are higher, as well as number of spectral bands are higher, there are so much storage is required. Today, at NRSC has the ground station. All our remote sensing satellites, we receive the data from at NRSC. So daily we get 10 gigabytes of data daily, and that we need to process. And in the next few, and we have actually the 5 petabytes of data in storage because it's last so many 30 odd years we are collecting the data. But immediately the jump is like this. Next 5 years, it will become it will become in fact 20 to 30 petabytes of data. Daily content itself is more. So the challenge is not only storage. Storage is one thing, retrieval is another thing, processing. These are all computer science challenges. In fact, data, it's a very big data. In fact, it's a big data challenge. Even if I want to retrieve an image out of this so many petabytes of data, you need a powerful algorithms to
retrieve. Yes, sir.
Yes,
with this storage size.
Right, content-based. These storages are today available, and then we have very well managed. But content-based image retrieval systems and all kind of things are powerful systems are required. In fact, not only algorithms, even the system should be much faster.
Correct.
To handle. So you can just imagine the high resolution data today, Cartosat 3, it is 64K by 64K, one image. Normally we talk about 512 by 512 and like that. But today's images, if you talk about as a one single satellite image, is 64K by 64K. 64 into 64, that many megabytes it will come. So that is the kind of data what normally we handle. Daily we receive the data and process and disseminate also. So the state-of-the-art computer systems are available at NRSC data processing facility. It's a very huge facility, in fact, because it is all automated. The data comes and processed and received, and it is disseminated also and stored anyway, archived. All these things are happening daily in an automated way. So much software development, so many algorithm development, and so much computer science behind, because hardware, software, as well as the security. Another problem is security. The data security is highly important because you are dealing with public relations, like data disseminated freely. But you need to have that security that your archive should not be exposed to any third party, once again. So there are so many things built in within this full circle of data reception, processing, and dissemination. Right?
Yes, sir.
Yeah. So this is
Thank you.
actually this is actually the spectral resolution. And then spectral resolution, what I mean is here just given 0.4 to 0.7 sliced into 0.4 to 0.5, 0.5 to 0.6, 0.6 to 0.7, blue, green, red, and near infrared, and then far infrared follows from there. Then this is the spatial resolution once again. List 1 camera is 72 meter resolution, list 2 is 36 meters, and list 3 is 23 meters. So you can see in the various resolutions how it looks. And here also one more example. You can see that pan 1 meter, if you see that roads are seen very clearly, buildings are seen, and like that. 2.5 meter. Why pan 1 meter is actually the Cartosat 2. Pan 2.5 meter is Cartosat 1. And pan 5 meter is in fact resource set. Like that, the various things. And you can ask that to see why all these things are required. There are so much data. See, each one has its own applications. Like the low resolution data is required at one time. You wanted to see India as a drought monitoring. Then you need a full India at one time. You don't need 1 meter pixel and all. There, even 200 meter pixel, 1 kilometer pixel also is okay because drought. Overall, I am concentrating on the drought monitoring. Whereas when I wanted to do a mapping, I need 1 meter resolution. Whereas resource monitoring, like agricultural fields and all, which I wanted to see, I can go with 23 meters, 36 meters, or 76 meters. And WIF's wide angle, wide imaging sensor, 188 meter, very large coverage, full district I wanted to see, or full state I wanted to see. So various things are required. Multispectral is required for crop monitoring and all. Black and white is required, high resolution for mapping. So there are various applications for various resolutions. And radiometric resolution to explain, this is a 24-bit image. And this is an 8-bit image. That is not too much of difference when you talk about. But when you see a 16-bit, it's a 4-bit image, 16 color. And suddenly it is a 2 color. So the same image, but the resolutions in terms of radiometry resolutions are different. So you have a lot of changes. So everything is important in terms of resolution. Then temporal resolution, when you talk about, see, it's spring, this is the image on a particular area, whereas summer, this is the image. So you can see the total canopy is changed in terms of ground canopy, in terms of coverage, as well as the crop. So you can see that both are different. So we need both images, spring as well as summer. So this is called the temporal. So that is all about the resolutions. Today you wanted to show Cartosat 2 image. It is actually 0.8 meter. Now you can see the big buildings and their shadows. So this is the power of high resolution satellite. So you can see a car as well as a road and multi-story buildings. This is also required for the mapping either way. And here why I took this image is there is a challenge involved. You can see the large shadows, no? So these shadows, behind that there is an image in fact. So there is a challenge in enhancing the image within the shadows. So that itself, nobody has addressed earlier that in the image processing or image enhancement, when you talk about, nobody talks about that simple contrast enhancement and all, you do it, but this is the certain challenges are there. One can work on those things. How to retrieve the information in the shadows. Shadows are not totally dark. Here I have depicted like that, but otherwise there is an information which you need. When I take a mapping, no, I cannot abruptly cut the road here because of the shadow. I have to get the information and then out of that. So this is another challenge. Now coming to the basic processing levels, you can see that there is, as I told, active and passive sensors the satellite gives, and data acquisition on the ground station, then data processing. Here I said data and auxiliary information. What is this auxiliary information? Auxiliary information is satellite ephemeris. That means its position, its velocity, altitude, they are all called the ephemeris information. Unless you know that, you cannot process the image because we need that information. Like satellite has certain orientation, roll pitch here, these are all called the auxiliary information. Then the data processing starts, pre-processing and radiometry and geometry. If you see that top to bottom, the information will be increasing. It's the increasing side of the information. Once you have a basic geometric correction and then overall image is clean, then you go to the value addition, which is actually the digital elevation model generation. You can do maps, you can do and merged products you can generate and classify, and mosaic and geophysical products. So all those things are called the value additions, and you can archive, browse, and disseminate. This whole diagram is actually depicting what NRSC's domain is. What we have: a ground station, we have a data processing facility, we have dissemination, and we have a remote sensing applications area, which they generate many the classified products. Hope you have got a picture of what actually comes to the ground at this stage. Okay. Now we will go to this satellite image processing tasks. So when you talk about pre-processing, let us say pre-processing involves, see, today when I say high resolution data, now satellite links are not supporting the data rates, what SAR data or high resolution data, whatever data comes, they are in terms of gigabytes. So what we do, we need to do, today's links are not sufficient, so we do the onboard data compression. Okay, and as soon as it is compressed there, and then maybe 1:3, when you compress, after transmitting to the ground, you need to decompress first. So onboard there is a pre-processing, and not only compression, there is an encryption, decryption, because the satellite ground station, when you transmit the data, only our ground station is allowed to receive that. Any other ground station, if they wanted to also receive, they need to have that encryption key there. So data is always encrypted so that nobody else will be receiving our data unless it is licensed. Because we have licensed to several people where they pay us some money, then only we give the. Yeah, so encryption is another thing. Then data compression is one thing. There are so many pre-processing steps on board first. Then on ground, we need to do those things. That I'm not covering as data compression, decompression. That is another topic of interest, which you may be aware. Then comes the radiometry and geometry and restoration. So this is the basic thing which we need to do before the data is put into use. Then value additions, which I already told. So now let us talk about the radiometric distortions first. Why we need to do the radiometric distortions? So we have a CCD camera on board. So CCD is charge coupled device, which has a response characteristics. That means for a given input, it gives you an output. It is after all an electronic device. So what happens? There are 4K detectors on board. Every detector will not have the same response. It's because all are electronic devices. So any detector, you give an input, it will give an output. So there will be a curve, or there is a transfer curve that for input versus output, this is what response it gives. That means for a low input, high input, this is the curve. But what happens, in each detector has different responses, even a slight difference. What happens in your classification, it will have an effect. Suppose water is there. Water, I expect everything will be only 1 gray value. Then only I can recognize that as a water. But because of detector responses non-uniformity, I get different responses even for a water. So you need to normalize. So that is called the detector to detector photo response non-uniformity. So this is the key to it first, which we need to do it. Then, since it is an electronic device and satellite can be there on board or in the space some 10 years, any detector can fail anytime. So when detector is failed, that response will be almost either poor or zero. So you will get a dark line when you compare to the both sides. So you need to have a detector failure or degradation corrections. Then as satellite is moving and then you are taking the pictures, there will be a motion blur defocusing. So all these things are to be addressed in the restoration, because you as a computer science background, you will be definitely knowing there will be a transfer function for any of the signal reaching to a particular destination. One signal is input to a system, and output will be a convolution of the transfer function and of the input signal. So unless you know the transfer function, you cannot get the replica of the input signal. So you need to have some restoration or transfer function, and the defocusing, the motion blur and all, you need to take care. Other effects are not so much important. Atmospheric effects in certain bands, they affect, but that has to be taken care. And then noise is another prominent thing, because photon noise is a prominent in the image that we need to take. Sometimes transmission losses and data compression, decompression. Because of all these things, you need to do a first radiometric correction. So now you can see this image. First image, because of radiometric non-uniformity, you can see each line you are seeing vertically, there is some discontinuity because each detector has a different response. So now that is corrected through a standard response, and right side you can see that is very uniform. So you can use this for the interpretation or classification. This is how do we do this? This is done in the lab before sending the satellite or before sending the sensor. What we do is we give a constant response to all the detectors and get the curves and normalize to a particular response, derive some lookup table and keep it ready. So then tomorrow, after the satellite is launched, using these lookup tables, you can correct it. So this is a simple principle. You can see this is the Chandrayaan 1 hyperspectral image. Raw data you can see it's totally unusable because of the detector response non-uniformity. Then you can easily say that our right side we have already corrected. You can see that today we do this. Even recent trend is hardware based onboard correction. Also we do these radiometric corrections. Here you can see that there is a detector response or failure, not failure, actually degraded over the time. If detector degraded, you can see that response is very poor in certain cases. So that also we need to correct it. This is normally you don't find any in the image processing book or something like that. These are all specific to the satellites. Then once the radiometric correction of that nature is done, then we need to do a restoration. As I said, noise as well as motion blur is the prominent thing. You can see the right hand side. We will detailed radiometric distortions. We will go in detail later on, but you can see that mathematical model for the restoration. So MTF, that is modulation transfer function. For the top figure, what I have given you, this is the imaging elements of the sensor. It has atmosphere, it has imaging optics, it has detector, then A to D converter and compression, then platform motion and platform attitude. These are all the components. So major things which are affecting is optics, imaging optics. Imaging optics transfer function we already know in the ground itself that we can use it. Then a detector also it's fairly known. Only unknown major thing is the motion. Because you remember what I showed you in the image acquisition modes, step and stare and push broom, stereo. So depending on its motion and all, the blur also will change. So those things you have to model. And other one is this motion you have to characterize for each satellites or for each sensors. Now in the frequency domain, this will become a multiplication. MTF optics into detector into motion, which will give you the net MTF. This is the net transfer function which you need to use for the image restoration. So this is the image restoration. If you see that Cortesat 2 image, the top is original image and bottom you can see that is a restored image. Restored image is, how do we get it? You can see that this is a general spatial response of imaging system. As I told, GXY is equal to FXY into, or not into, it's convolved by HXY and plus NXY. In the frequency domain, GUV and in is equal to FUV into HUV plus NUV. Noise anyway we can approximate. So finally what we need to do, we have to find out the HUV, that is transfer function. Okay, this transfer function, whatever I told you, that way we derive, and using the Wiener filter, not inverse filter, in pseudo inverse, there are various ways of deriving restoration filters, but finally we use as a Wiener filter, and take the noise to signal ratio parameter, tune it, and then use it for the restoration. So these are the various images. You can see that left is original image and right is the restored image. In fact, these are, you have to take so much research into it and then see for each sensor which exactly noise to signal ratio and then which transfer function suits and all. We have to experiment in the beginning and then use it for the final data processing. Now you can easily see that how best we could restore these things. Left side and right side, the top image, you can see very details, and these are the restored images. Then the third one is the noise. This is another problem, because as you go to the higher and higher resolutions, the signal dwelled at the detector is very, very small. So, but the noise is same. So photon noise of the detector is same, but signal reaching to the detector is very small, because the time what it gets for getting a signal is very, very small for the high resolution, because it's quickly it has to take. So there's a lot of noise. So what we do is we use the adaptive low pass filter in this case, signal dependent photon noise plus quantization noise. Noise characterization first you have to do, estimation of signal level and total local variation you have to do, then adaptive signal estimation in spatial domain. So you estimate noise from the image itself, that is noise variance and all, and use this to estimate G cap 1 minus W into these things, which fairly works for the satellite images what we are dealing with in this case. You can see that band 1, band 2, band 3, each band or each spectral band will have a different kind of noise effect. So you can see that band 1, band 2, band 3 and band 4. So easily you can see the noise removal algorithm also fairly worked very well in this case. And this is for the Chandrayaan moon impact probe images. So you can see there is a dot periodic noises. And then we have worked out, or we have experimented frequency domain filtering, Butterworth low pass filtering plus notch filter together through adaptive median filter. So various filters we have worked, and then we got very good images after removing the noise. So today other trends when you talk about in the restoration, wavelet based image restoration, people try, and image denoising using curvelets, edge preserving, blind deconvolution techniques. These are various things which current trends in fact. Then coming to the geometry, so what are the other distortions present in the image in terms of geometry? Why at all there are, why we need to do this data processing in terms of geometry? See, when you talk about satellite imagery, it is after all what only a pixel gray levels, matrix of gray levels, right? So when you talk about matrix of gray levels, if I give you an image, you cannot say it is actually the Coimbatore or Delhi or Madras or anything. Only when you tag the geo information to the image accurately, then only you can say this is this image. It's Los Angeles or Washington or anything. When you wanted to talk about, you need to attach the geo information, that is the latitude and longitude, and that too with a high accuracy. Like all the Google images or navigation, unless it is accurate, you cannot navigate. You cannot use it for navigation. So how do you do that? You use all the information as the satellite images. What all the information you need to get it, you should get it from satellite, and you understand also what images have gone through the geometries. So you correct it, then only you get a very high accuracy in terms of geolocation. At the end, you have to tag it to a geolocation, a pixel to be tagged to on the ground. Then only it is a valid image. Otherwise, it is a simple matrix, just gray values. It has no big meaning. Okay. So now What are the geometric distortions? When a satellite is going through in a motion or in an orbit, Earth is rotating. So you need to consider that Earth rotation effect, because you assume, like frame, when you take, there is no Earth rotation. Click in one small microsecond, you may be taking a click. That time there is no Earth rotation. But when I take push broom, you take line by line. By the time you take next line, next line, next line, Earth is already rotating. But you assume that it is actually a square image. It is not. So since the tagging is different, because Earth is already rotated, so whatever pixel you are taking in the image, it is corresponding to a different portion of the Earth, otherwise as a frame image. Okay. Then at curvature, when you take a large portion of the image, like insert, you take full one third of the globe, you need to consider Earth curvature effect, because Earth is not flat. You assume Earth is flat, but Earth is curved. So because of that, there will be a lot of distortion in terms of assigning latitude, longitude. Then there is a terrain effect. So Himalaya is 8 kilometers up, whereas other things are mean sea level is 0. So between them, there is a lot of scale variation. When you are taking the image, both you cannot put it in the same scale, because that already altitude, it has imaged very closer to that, like 600 kilometers minus 8 kilometers you are seeing. So its resolution will be little better there. All these terrain effects you have to consider. Then platform related, when you talk about attitude, attitude means what? When you take a moving body, it has 3 components. It is like aircraft, when it is moving, it's a nose up, wing up, and rotation. So nose up, nose down, it is actually roll. Wing up, wing down, it is actually the pitch. Nose up and nose down is the pitch. Wing up and wing down is the roll, and the rotation is yaw. So all 3 effects are there when for the moving body. So when you take a picture, depending on its satellite's orientation, the line will be changing. So you have to understand that and then correct it. And the orbit. Orbit, simply if I say 900 kilometers, it will not go in 900. It can be 901, 902, 903. But when a small change is there, when I talk about 0.25 meter resolution, definitely if 900 kilometers become 905, accordingly, h tan theta, the subtended angle on the ground, will change. So it becomes 0.25 to something else, 0.23 or 0.28, depending on the altitude. So orbit is one more important thing. When orbit is changed, velocity also, like h is changed, v is inversely proportional to h. Velocity is inversely proportional to altitude. So obviously, the across track, that means in the swath side, across track is defined by the altitude. But along track, as satellite moves, velocity is defining the resolution in the along track. So velocity variations we need to consider. So these are the scene and platform related. Then sensor related, scan non-linearities. We are thinking that scanning is linear, but sometimes it can be non-linear, little bit. Non-uniform sampling rate. That means you are uniformly sampling, we are thinking, but if there is a non-uniformity, you have to consider. Then panoramic view due to the tilt. If I am seeing straight on the down, I will get the 0.25 meter. But if I tilt by 10 degree, 0.25 degree meter becomes something else, 0.5 or 0.3. Because slantly, if I'm looking, I'm seeing very big area. No? So the same CCD looks large area. So panoramic view due to the tilt, which you have to consider. So sensor mounting angles and alignment, also you have to consider. You are thinking that sensor is mounted at 5 degree. If it is 5.01 degree, your calculations are wrong. So you need to do that. Then map projections. See, Earth is actually all the maps are in the 2 dimension, but Earth is a 3 dimensional. So the 3 dimensional projecting to 2 dimensional, there will be error. So you have to have that map projections, errors. Then datums, because if you wanted to do a projection, you need to have a particular datum. So we have WS84 and all various datums. So these are all the things which you need to consider for correcting the imagery. You can imagine that how much normally it is involved work in the satellite image processing. So here I just put roll means how the image looks. it's a little enlarged. Pitch is how in a long track pitch. So sometimes lines are closer, sometimes lines are farther. A roll, there's a wing up and wing down. So sometimes this side, sometimes right side, sometimes left side. Yeah, because of the rotation, sometimes this side more, sometimes this side closer. Then a small scale, if it is wobbling kind of thing, all these things effects you can get it. So in a simpler way, how do we correct this? You don't need to go to this is a highly mathematical, but you don't need to understand so much. Just conceptually think that I need to connect the image point, whatever is imaging, to the ground point. That is what is my task. Then my task is achieved. So that means for each pixel, I need to assign a ground. That means latitude, longitude. For that, what we use a simple mathematical formula is collinearity conditions. What we assume here, image and satellite and ground are in one line. That is a mathematical approximation that is called collinearity. So this is a collinearity condition which is involving all the 3D transformations, three-dimensional geometric transformations, which you don't need to go too much on that. Only things you understand is X and Y are actually the coordinates of image in the focal plane. That means in the camera plane, F is the focal length. XA and XS are actually one is satellite position, XS, XA is the ground position, M is the transformation matrix, S is the scale factor. It's a simple mathematics. So this is a three-dimensional geometry. That means going from ground to image or image to ground. Image to ground, that means XY to XA. XA is the ground point. XY is the image point in the camera. So this is called a ground to image or image to ground transformation, which involves all the geometry, which otherwise involves you can see that it's a three-dimensional matrices. RO is actually the rotation matrix for orbit, rotation matrix for attitude, rotation matrix for the angles. All those things are involved. So you don't need to worry. This equation is relating image and ground. What are the uncertainties in this? M is the transformation matrix. Whatever auxiliary information we know to a certain extent. We will not know for full extent because satellite roll pitch, position and all. To some accuracy we know. With that accuracy, this equation is valid. And we call it as a system level accuracy. Suppose for a particular satellite, I say system level accuracy is 500 meters. That means I can relate image to ground or ground to image up to 500 meters accuracy. So how to correct that 500 meters to bring it to exactly with 1 meter or something? Use some ground reference. We call it as ground control points. Once we use the ground control points, M will be updated and this equation will become more accurate. That is all what you should know it. Okay. So this is more geometry in this. Actually, how the pixel is related to the ground. That is C is the ground point, and then A is the image point, and B is the satellite. So these three are in collinearity equation. So now you can just see that how the image is corrected. It is rotated here. Better is this. Radiometrically corrected image is like this. Geometrically corrected image is like this. Why? Because it is after earth rotation and all corrections. This line is like this. And this is actually the right side is actually corrected and it can be overlaid onto the ground accurately. Left side you cannot overlay because at one point if you match, other point it will not match. But right side, after everything is corrected, now this can be used as a map. So this image you can see now, I have put everything together in the left side. You can see that the first one, just wait, raw image. This is the raw image. Then radiometrically corrected image. Then geometrically corrected image. Then orthorectified. Orthorectified, I will come back a little more. But this is how whatever I told, all these processes involved in this case. And what I have not told is the second one, right side, there are certain specific cases that there is a arrays. We don't have 12K array, a single array in CCD. What we have done in Cartosat 1, staggering array. That means 6K, another 6K, they are staggered by some 5 elements. So that's how you can see that first raw data is seen as blurred by 5 pixels that we have corrected. So that is the stagger correction. And misregistration down, if you see that some kind of red, green, blue, they are not identically put together. So you need to have a registration. So that is corrected. Then there is a too much in the aircraft image, rightmost side, too much of wobbling. You can see that line has become like a wave. So that is corrected. Otherwise 27 is not seen. Now you can see that 27 is seen. So this gives you a proper idea of the final image correction and data processing in a simple way. It is only a basic correction only I have told right now. So you can make use of this image for any application. Is it clear, madam?
Yes, okay, sir. Yes, sir.
So that next one is just to give you some idea that hyperspectral image processing, because the hyperspectral is the current trend. You can see that what all the advantages you have hyperspectral. You can do the material identification, environmental aspects, monitoring health of the plants. Why? Because you can see that any signature on the earth has certain spectral characteristics. That means wavelength versus reflectance. You can see this. See water between 0.4 to 0.8, how it behaves. And this clean water as well as water with phytoplanktons. Their signatures are totally different. So at different spectral bands, you get different reflectances. You can see soil reflectance. This forms a basis for the hyperspectral analysis. Now you can see wherever dips are there, wherever rises are there, if your narrow spectral band is picking up that, you can use either band subtraction, band division and all. You can very better way discriminate those features. So best feature detection you can do with the hyperspectral, like healthy vegetation. So you know that at which wavelength you can pick it up much better, which wavelength it is absorbed. So each feature has particular spectral signatures, which you can use. Spectral library, actually for hyperspectral analysis, spectral library will be available, which you use it as a basis and then use all the classifications. So now you can see that agriculture, it is a very good aspect. Biological and chemical detection, precision agriculture, there are so many applications for, because here you have some 512 bands and all. Different bands will give different depending on the spectral signatures. You can take a particular band combination to analyze a particular feature. So this is the best way, and there is a lot of challenge because the data handling also is more, classification, best band selection is also involved. There are many challenging topics in hyperspectral. So this is actually the basic portion of satellite image processing. Now we will quickly go to the certain value additions because stereo image processing is one thing which is challenging and which is required, because what happens, you need for any geospatial applications or mapping and all, you need the terrain undulations, terrain height, which is called the digital elevation model. Digital elevation model or 3-dimension, third dimension, how do you get? For any third dimension, like we have a stereo imaging in our own naturally. Biologically, we have 2 eyes, and each eye sees a different angle, subtends different angle on a particular target. And in the brain, it will be assimilated as the third dimension, because wherever the both rays intersect from left eye and right eye, that is the height point or depth point, what we can say. That is the same principle we use for the stereo imaging as well. Same, exactly the same principle. So stereo imaging, what is the prerequisite? You need 2 images, at least 2 images with viewed in 2 different angles. So that can be with one satellite also. You can do one day you view and come to the next day and the different angle you view. Or Cartosat 1, in the same satellite, you have two sensors which are mounted at two different angles. Continuously you take, it is an operational stereo. Like Chandrayaan 1 also, you can take 3 images simultaneously and then get a stereo imaging. This is the kind of stereo imaging. So you can see this is called the stereo pair. One is viewed at 17.5 degree, other one is minus 18.3. You can see that they look entirely different, but that differences are required to capture the parallax. Once you take the difference between them, the parallax, if you go to the stereo concepts, the parallax, that is the relative displacement of the feature in the both the views, will define the parallax. That parallax will give you the what is its height, and through mathematical model you can get the exact height. This is actually the Chandrayaan 1 triplet, nadir view of a particular crater, fore view and aft view. Nadir is 0 degree, plus 26 and minus 26, the 3 angles. And this is another crater. You can see that same crater, how it looks at three different views. And this is required for us to generate the digital elevation model. So this is a basic block diagram of stereo image processing. You have a stereo pair, you have a ground control point collection. So some reference, I told that the reference is required. And this is the model, center point, what I told, ground to image and image to ground models. And space intersection, what I told, given 2 points in 2 left and right images, how to get the height. That is called the space intersection. Then once you get on and the down portion is the core image processing task. That means you need to get in both left and right images the same points. Then only I can get the height. See, you have to identify, like I told, the same point in all 3, I should get it where they are. How do I get it? Through computer automation. I match it through correlation and all, and then get the same point. Once I get the same point through mathematical model, I can get the height. So the bottom box is purely the image processing box. Then on irregular points, we get all these heights. Then you make it interpolation and then make it regular and do the digital elevation model. So this is like a Chandrayaan 1 left image, nadir image and aft image. What we do in a hierarchical matching in a pyramidal generation. So that means the high level, the whole image, we compress by twice, 4 times, 8 times, and 16 times and 32 times. So this hierarchical image matching will be the more easier way to do it, because at the last level, 32 level, I can directly match and slowly propagate to the last level. Otherwise, if I take directly this one-to-one match, even a supercomputer also will take a lot of time to do for each pixel, because if you talk about these images, it is running into 1200 kilometers or 800 kilometers, and per kilometer, how many? Because 5 meter is the pixel size, and so many kilometers, so that many pixels will be there. And the swath also will be some 20 kilometers and all, which will be a lot of image. So you cannot match at first instance straight away. So I have to go through a hierarchical matching approach. So this, in fact, we have developed. Now, what are the challenges when you talk about matching? Multi-temporal seasonal changes of ground features is a challenge. If it is not viewed on the same day, 2 different days, if you are viewing and getting the same, then ground changes is another important aspect. Then different view angles. One is seen at nadir, other one is seen at 26 degree. So there is a lot of difference which you need to address. Scale changes, that means similar. One is seeing at one scale and then the second one is seeing in a different scale. And radiometry and resolutions. Even when you say that slant range, resolutions are also different. So all these things you need to address. So matching methods and matching entities. This is just academic interest for you. So there are so many matching methods: area-based, feature-based, symbolic. Then similarity measures are there: correlation, least square matching, mutual information, cost functions, and these things. And match entities, gray levels you can use, interest points you can use, edges you can use, relational description you can use. And the feature spaces used in this raw intensity, you can use edges, salient features, statistical features, higher level features, matching against models. So there are so many, there's so much research in this image matching. Today, nobody has achieved 100%, but anyway, closer to the 100%. People are, this is a research still going on, and many papers are there, and then many papers are coming also. Similarly, matrix and set strategies. So we have selected the hierarchical technique. I think we have worked around 10 years to generate a full-fledged software. Given a Chandrayaan-1 triplet imagery, finally it will give you the digital elevation model. Even for Chandrayaan-2 today, that is the same thing being used. And Cartosat-1, the entire India or globe, we have generated digital elevation models. So there are feature operators, scanning, edge detectors, and shift Froshner operator. Then similarity metrics, if you talk about mutual information, is one thing which is the best one to use. So this is a greater research potential topic. These are the hierarchical matching components. I think we will skip this. Is a template matching where left and right images, a small portions you take and then match. Wherever correlation is high, you can take, that is the match point. So once hierarchical matching is achieved, I will tell you what are the various components in the hierarchical matching. See, first what I do at the 32 level, I will select some interest points of interest, and then use a digital correlation and match on the left and right images. Okay. So then in the second level, that is 16th level, once again you collect the interest points. Now you have to match in the next right image. How do I match? I use the previous level match points into 2. This side is only into 2. So I have to just make a local mapping between the previous level matches. Previous level, I know that what is the left image, what is the right image matched. I make a small polynomial equation. So for any given point in the level 16, the same local mapping is valid. So now I transfer this point to the next point and use the digital correlation. This process goes till the end. So last level I will match it. So once I get the match points in both left and right images, then we use the mathematical model called space intersection. As our eye, whatever principle I said in our eye uses, wherever in the space it intersects the same. Say, take left image point, right image point, wherever they intersect on the ground, that is your height. So this way we can generate a digital elevation model. Now you can see that the entire image, 30 kilometer by 30 kilometer image of Cartosat-1, we have generated. Right side is the image, left side is the digital elevation model. Wherever bright is there, it is the high elevation. Wherever dark is there, it is a low elevation. You can see in the right image, it's actual image, you can see this C portion, the C portion. Remaining thing is the digital elevation model. So this is more important. And this is our Gangtok highly hilly region. This is another digital elevation model. This is a glacier, Siachen. It's a digital elevation model. And this is the entire India. From Cartosat, we have derived the digital elevation model, these things. Madam, you wanted to continue or it is already 1 o'clock?
Yes, sir. Maybe you can just wind up with the 1 or 2 slides, sir, and then probably right. 1 or 2 questions we can take.
Right, because the value-added portions I'll quickly skip so that
yes, sir, that one.
We can have
that one. Yes, sir. The value-added you can just add on.
I'll just go through that, but not too much of explanation.
Yes, sir. Yes, sir.
You will get some idea. Okay.
Yes, sir. Yes,
this
sir.
Is the digital elevation model, that is 3D. Okay, fine.
Yes, sir. Yes, sir.
In fact, this you can download from NRSC website or Bhuvan website freely. So for your use. Okay.
Sure, sir. Sure,
so these are the digital elevation model applications, mapping and then perspective geometry and all. And the digital elevation model is required to generate the ortho correction. Whatever maps, Google Maps or our image maps or Survey of India maps you say, they are called the ortho corrected maps. Ortho image is what, if you see orthogonally top to bottom, like A, B, C, D, E points, if you see that, how they look in the perspective geometry in the right side. So because whatever satellite imagery, we look A will look small a, B will look a small b, but they are all different distance. So that how it looks in the left side to right side, cone is looking like this, cylinder is looking like this, building. Normally we wanted to see cone as cone like this as a orthography. So to do this, we need the height information, which is digital elevation model, whatever we have generated. Once digital elevation model is there, then the ground to image is applied, and then the digital elevation model projects exactly where the point is. So this is how ortho image is generated and geocoded. Geocoded is without using any height. So there is a lot of deviation from the original map, if you see this. Whereas once I use the height and then correct it, the deviation is removed. Okay, this is all about geometric correction. Now, once you have a digital elevation model, you can have this ortho correction and you can have a perspective geometry. This is on a Chandrayaan-1 digital elevation model, perspective geometry. This is the Chandrayaan-1 digital elevation model as well as contours derived. And this is an image map we have generated from the Chandrayaan-1. This is the highest map what we have today. Nobody has at 25,000 scale maps we have generated. This is a very small crater. If you see on the left side image, it looks like a bulging. Actually, once you use the digital elevation model, actually it is a false illusion. It is actually down. It's a crater. So image registration, which I already told, for a change detection, different day images you have to register. This is another topic which you can go. You can see this, how it is changing. In some day, this oil bunkers are not there. Someday it has come. So unless you put it a registered way, you cannot get this view as a change detection. So image registration is another important topic which we will do. Then image mosaicing is another one which normally do. I will not explain this, but you can see that images are required at 3 different days and adjacent. But we want actually the one city, if you want fully, you need all 3 images stitched. So now you can see that there is a stitching, but there is a radiometric difference also now corrected. So this is what about the image mosaicing. This is another challenging task for high resolution image. If these are all buildings and all, when you want it to stitch like that, it is impossible. But through a graph theory approach, we could do much better. So this is image mosaicing. Then image fusion. That means you have a high resolution image in the right side at 5.8 meter and low resolution image, high resolution image at 0.8 in the left side, panchromatic, and multispectral coarse resolution 5.8. If you wanted to fuse them, there are techniques. You can see that the last one bottom, how best it is fused. It has put all the color information as well as the high resolution information. You can see here, list 4, it is actually 5.8 meter, and Kato 1, it is actually 2.5 meters. Together, you can see the 2.5 meter color merged product. So this is another area of interest, data fusion. So this also you can see that. And then coming to some of the challenges and research areas, as I told, enhancement of shadowed portion of the HR high resolution image, image matching and registration, big data analytics, automatic feature identification, data fusion, image simulation for various satellite missions, super resolution, digital surface model. Whatever we get today, whatever I am saying is DEM. It is actually digital surface model. Satellite sees digital surface only. From there, if you wanted to generate digital elevation model is without all the man-made objects and canopy and all, only bare earth model, what we call. That is another challenging topic. High resolution image mosaicing, 3D city models, cloud distributed computing, microwave data processing. These are some of the challenges. Other topics on EO data processing, many I have listed here. And some applications, if you see that, I told fusion, registration, mapping, agriculture, cartography, ocean, bio, geology, rural, urban, NR census, climate changes, water resources. These are various remote sensing applications. Then just to give a brief on planetary and science missions of ISRO, Chandrayaan-1, we had this many payloads, Chandrayaan-1 payloads. So each one has worked and then gave some, these are the, in fact, whatever Chandrayaan-1 is covered only this much, and polar this much area it is covered. And the data is archived in PDS, what we call the planetary data system. All the planetary data has to be archived in PDS. This is a big subject which we can give one more talk on that. What is planetary data system? And that is there in Indian's Science Data Center, that is at ISRO, that Bailalu, Bangalore. So we have archived all the data sets at ISSDC, what we call Indian Space Science Data Center. So this all the data, all the payload data is archived. Some of the findings of Chandrayaan-1, in fact, M3 has helped to discover the water. That is the first thing, and confirmed certain hypotheses. Then produced some 70,000 3D images, and it has imaged actually Apollo 15 and 17 landing sites. The polar area also mapped, and in C1XS has given a good confirmation of presence of calcium and measurements of magnesium, aluminum, and iron, and also detected 24 weak solar flares. There are many good findings are there. Then Mars orbiter missions, these are 1, 2, 3, 4, 5 payloads are there, launched on September 14th, or so it has reached Mars. Otherwise launched on 5th November. And these are the Mars images. And some major findings are very recently that has taken several high and coarse resolution images for topographic analysis. And it has discovered dust storms on Mars, which can rise up to hundreds of kilometers. And there is a payload, Manka. It has actually measured the carbon dioxide, nitrogen, carbon monoxide, and oxygen, which are varying with height. Then AstroSat, India's first dedicated astronomical satellite. It is launched in September 2015 for study of cosmic sources using multi-wavelength broadband X-ray studies. These are not imaging payloads except UVIT. And there is a major finding very recently that multi-wavelength satellite has detected an extreme ultraviolet light from a galaxy, which is 9.3 billion light years away. It is recent finding which is created very good impact in the science. And the Chandrayaan-2, we have 6 payloads in the orbit, which is they are working right now. And I think it has given a lot of images. You can see this is the Chandrayaan-2 3D image, and these are some images. And other than this, there are other science satellites which are YouthSat, Megatropics, which are archived the data sets for the planetary and astronomical data analysis. I think this is all what lastly I quickly gone through. I think we will finish at this stage.
Maybe we can take 1 or 2 questions, sir.
No problem.
Okay. Probably if 1 or 2 questions. That was an inspiring talk, sir.
Okay, thank you.
Good afternoon, ma'am. Good afternoon. I'm Vanitha, ma'am.
Yes, ma'am. Please proceed.
Sir, good afternoon, sir. I'm Vanitha.
Yeah, good afternoon.
There are many questions because it is highly contented, sir. The one thing is we are not seeing the SAR image processing and temporal resolutions, I guess, sir, because we have spent our time on geometric and radiometric imaging. Am I correct, sir?
Yes, optical images only I have concentrated. As I told, SAR image processing is a big subject once again.
Okay, sir.
And it has to be taken as a, like today I have taken as optical remote sensing kind of thing.
Okay,
like SAR remote sensing or image processing is a big subject once again, because there are so many signal to image conversion itself is a big topic there.
Okay, sir. Okay.
Then
sir.
after that, speckle removal and then conversions and all, it has its own way of doing it. So that's why
Okay,
I'm not covered, because within the limited time, whatever I could quickly cover, I have covered.
The second one is which is very generic, sir. When you land the position the satellite in the orbit, and how will you set up the SWAT, sir, initially?
No. SWAT is prefixed already.
Okay.
Before satellite is launched.
Okay.
We know what is the satellite, what is the altitude, and what is the SWAT. Everything
Okay,
is fixed because if my resolution is 2.5
Okay, sir.
and I have 12K detectors, I get only 30 kilometers SWAT.
Okay. Then
Yes.
if the satellite expiry is anything, the tenure, sir,
Yes,
because
we
the
define
energy
satellite.
point of view,
Yes,
depletion
sir.
of the sensors, yes, sir.
Right. We define satellite lifetime as some 3 years, 10 years, like that, because depending on the
sir.
fuel what it has,
Okay, sir.
and depending on its deviation, what the fuel will do when the satellite orbit is slightly deviated,
Okay, sir.
every 2-3 days they correct it to the correct orbit. For that, fuel is used. So they calculate the fuel will come 3 years or 5 years and all. Sometimes the corrections are not too many required. Like Mars, we managed for 6 months the lifetime, but today 6 years also it is working. Because few corrections are not required and it is working very fine. Then the fuel is there, so it can work without any problem.
Okay. Great, sir. Great. Okay, sir. Even if we are getting insert and lot of images from satellite, why we are not offering to the public use as like Google is a private organization giving live maps to the public, sir? Is it confidential? Anything, sir? Policies?
No. There's nothing like today. Like maps are confidential. Today we have a policy. I think recently I saw an article that all the geospatial or map policies have changed, where anybody can create a map and all. No, so that kind of thing. Otherwise, till now, 1 meter resolution should not be publicly given unless there is a permission and all those things. But otherwise, up to 2.5 meter and all, we were giving. So slowly the things will change. That policy is our policy only. Certain things are specific to our.
Thank you so much, sir. Thank you for the patience.
Okay, you're welcome.
Thank you, sir. Thank you.
Thank you, sir. I think probably we can just take the questions offline or through emails next time when we take
some other topic when we discuss also. If some other thing, if you want, we can make another topic, because I quickly have gone through. Only stereo image processing alone we can talk one day.
Yes, sir. Yes, sir.
So otherwise, this will be only very generic, high level.
Correct,
you got it. Otherwise, geometric correction itself is a big topic, because I said because this is enough geometry and ortho correction and all those things. Even value additions.
Yes,
there are various ways like image mosaicing or registration.
Correct.
Specialized things are there. We can talk separately. But this is the overall high view, which now you can have any questions offline also. You don't you don't hesitate. My email is there. You can ask me, no problem.
Yes, sir. Yes, sir. And it's highly contented, sir, actually. Yes, ma. Over to Rajeshwari. For vote of thanks.
Nansudha here.
Yes, ma'am.
I'll just take over.
Yes, ma'am. Please take over.
Good afternoon, one and all present here. On behalf of Department of Computer Science and my own behalf, I deem it a great pleasure to extend a vote of thanks. At the outset, I would like to convey my sincere thanks to our correspondent, Dr. D. Batmanabhan, and Secretary Mrs. Geeta Batmanabhan for their support and encouragement in organizing such activities. My heartfelt thanks to Professor Gopalakrishna for his virtual presence today to share his expert knowledge on satellite image processing. It was indeed so great of him to spare his valuable time. Thank you, sir. My sincere thanks to our principal, Dr. T. Shanta, for her support and coordination. I also take this opportunity to thank our director, Dr. G. Radhamani, for her help in the successful organization of the meet. My gratitude goes to the head of the department and faculty members of Department of Computer Science. My sincere thanks to the student members and the supportive staff who are involved in the smooth conduct of this event. Dear all, life is not just a series of calculations and a sum total of statistics. It's about experience, it's about participation, it's about sharing, and it is something more complex and more interesting than what is obvious. So So always try to be a part of any great event that will teach you wonders in life. Thank you.
Thank you, Ma. Thank you. Sir, thank you so much, sir. Very kind of you. We'll meet again in some other
Yes, sir.
occasion, sir.
No problem. Yeah.
Thank you, sir. Thank you.